So let's think about a very basic function here, f of x equals x squared. It's a nice function to work with, but if we want to find its inverse, we would end up having to take the square root of both sides, so we would get x is equal to plus or minus root y. And the problem there is that because square roots don't have necessarily those unique values, that is, you can get two different things getting squared to the same place, like negative 2 and positive 2 squared are both 4, so square root of 4 is plus or minus negative 2. The equation x equals plus or minus root y is not a function. And as a result, we cannot talk about y equals x squared as being invertible, where there's a special designation for functions whose values are unique. That is, functions where every input goes to exactly one output. Those are what are called, well, not exactly one unique output. Those are called one-to-one functions, or in some other context, injections, where functions that are like this, that have unique outputs for every input, are invertible. That is, if you do not have unique outputs, you cannot have an inverse, because if you try to take the inverse, you'll end up with something that is no longer a function with two outputs for at least some inputs. And the way we can check this is with what's called the horizontal line test. In the same way that the vertical line test, that scanning through, showed us that if we hit 2 points, we had two outputs for one input. If we scan upward instead through a function, we will see that if we have the same output for two inputs, we're going to run into a problem, so the function is not one-to-one. In particular, we get this problem with things that have nice symmetries around the y-axis, so even functions are never one-to-one, and thus are never invertible. But let's get a quick example here of how we can quickly test this using horizontal lines. So for this example, we want to see which of the following graphs represent invertible functions, where for our first one, that looks a lot like an absolute value, which we know is even, but if we scan through that with a horizontal line, we're going to see that that has lots of problems. So that is not one-to-one, and therefore it would not have an inverse. Meanwhile, for the second case, that's a little bit less familiar of a function. We might be seeing stuff like that later. But even though it gets pretty horizontal, that line never evens out entirely, so we can scan all the way through that. We're always going to have unique outputs for every input, and that one would have an inverse. So, to be as clear as possible, A does not, but B does. Or at least, based on appearances, we should expect it to. And the last thing we're going to see for this section is a bit more with how graphing fits the context, I'll say, of inverses and invertible functions.